Okay, so first let's take a look at the homework. For homework, you were told that the tangent of your angle x is 2/3 and cosine of x is positive. Find all the 6 trig functions, right? So we already have the tangent of x is 2/3. And before we go into anything, taking into consideration that the tangent is positive and the cosine is positive, that means we are in quadrant 1, which means that everything should be positive. Okay, so again, like we saw in the last example yesterday, right, all of our values will be positive. We don't have to worry about taking the negative part. All right, so tangent of x is 2/3. The easiest thing to come up with next is cotangent. Cotangent of x is the reciprocal, so that's going to be 3/2. Okay, so right away, again, normally you can always find one immediately after you're giving a specific case, right? So we're given tangent, so we found cotangent. Now, the others might have been a little trickier. So we have our rational, I think that's, yeah, rational rule that tangent is sine over cosine, but we can't find one without the other, so that doesn't work. So there's no more reciprocal identities. There's no more quotient identities. That was the word I was looking for. So we're going to have to go to Pythagorean identities, right? So we have tangent and we have cotangent. So we can't use the normal sine squared plus cosine squared equals 1, right? That's off the table. But we have others. One of the others we can use is 1 plus tangent squared equals secant squared. All right, so we can find secant if we're given tangent. So we know that tangent is 2/3, so we replace that. Oops, not 3. So we have 1 plus 2/3 squared, which would be 1 plus 4/9, which gives me, if I make this common denominator, 9 over 9. So this gives me 13/9 equals secant squared. So we take the square root. I can't do the square root of 13, so that's going to stay square root of 13, but the square root of 9 is 3. So I have secant, right? I took the square root, so the secant is root 13 over 3. Let me make that look a little neater. Root 13 over 3. Because we have secant, I can figure out cosine, right, is the reciprocal. So doing the reciprocal, we get 3 root 13 over 13. Okay, you would have 3 over root 13, but remember we have to make that look neater. We have to rationalize that. Right, so if you told me 3 over root 13, I wouldn't mark you wrong, but I'd take a point off for not being simplified. Okay, so now we have cosine, tangent, sine. I'm sorry, cosine, tangent, secant, and cotangent. So now we have a few different ways to get sine and cosecant. I could get cosecant using a Pythagorean identity with cotangent. So let's do that. So my other Pythagorean identity is 1 plus cotangent squared equals cosecant squared. Oops, can't see that. Let me make this a little, zoom out. I guess I can't zoom out far. Okay, anyway, cotangent we know from before is 3/2. right? So we have 1 plus 9/4 equals cosecant squared. Now again, we're going to get a 13, but now doing the common denominator, we get 13 over 4 equals cosecant squared. So regular cosecant is going to be root 13 over 2. All right, so secant was root 13 over 3. The cosecant is root 13 over 2. And then for sine, we take the reciprocal, and that's going to get us 2 root 13 over 2. And there we have our 6 trig functions. Now, you may have used other methods to find sine and cosecant, right? But the first two, doing the reciprocal and then finding secant, all right, you're kind of pinholed into using the methods that I used here with the Pythagorean. Okay, but we didn't have to use the Pythagorean, a second Pythagorean. I could have used different methods. I could have found sine from tangent. Oh, excuse me. Tangent and cosine. Oops, I wrote something wrong. This should be 13. All right. So after you find that initial one, again, usually the first one, you have to use a certain method, right? But then after that, you have a variety of ways you can solve for the others, right? So there you have the 6 trig functions up there, right? So, in dealing with trigonometry, just a warning, most of the time we're not going to be dealing with nice numbers. We might be dealing with nice fractions, but you may see fractions with square roots and a lot of other things going on. All right, so that's just a forewarning for the rest of our trigonometry.
Well, I was doing the homework yesterday. Sorry, I thought you were done talking.
No, go ahead.
So when I was doing the homework yesterday, I'm here like doing it, and then I see that like I get square root of 13 over 3 for the cosecant. But then I'm like, this is wrong because it's always the opposite. We always get like the shorter number for the sine, and then we get like
right. Yeah, right. Because normally we're used to seeing pretty easy fractions over here, and then these ones being the crazy ones. But yeah, in this case, it was a little flipped. Any other questions?
Are we going to learn something new, or are we just gonna keep going over some problems?
Do you want me to go over more stuff like this? Because we're pretty much done with this. I don't want to spend too much time with this because there's quite a few other things to talk about with trigonometry. Unfortunately, we probably won't be done with trigonometry until like the end of March.
If you say we're not gonna, I'm good with it.
Okay. All right. So today, what we're going to talk about carries over to a few different things that we'll talk about in the future. Simplifying trigonometric expressions. So there's a few different ways that you may be asked this. You may be given an equation, right, with an equal sign, and they may say make the one side look like the other, or prove that this is true. We'll get to that eventually. That'll be next week. Another thing they may just ask you to do is just to simplify. All right. A lot of times we have kind of these convoluted expressions, these really lengthy trig expressions, and the behavior of the trig trigonometry with all the, the rules and the identities that we know, we can shorten it to, a nice, easy, quick one expression. Okay, so let's take a look. They may ask us to simplify. So here we want to simplify sine of theta times cosine squared theta minus sine theta. All right. So again, I probably said this before. Right, but anytime we see exponents with trig, they write it one way, but it can be viewed as two different ways, right? So if I have sine squared, I can write that as sine of theta squared. Okay, that's how you would type it. It's written like this, but you would type it into a calculator if you wanted to solve. You would type it in like this. All right. So here we have the sine cosine squared. Oh, what is sine? So we treat each one of these like it's its own variable. All right. So if I wanted to rewrite this, I could say something like y squared minus x, right? Sine is x, cosine is y. I'm just using that as a reference. We're not going to be doing with this, right? I don't want to be going back and forth between variables and trigonometry. That's too much, right? That's AP calculus stuff. You'll get there eventually, right? But we can treat this like we treat this, right? So here in this expression, xy squared minus x, I have a common term x in both of my parts, right? Up here, I have a common term sine in both of those parts. When we have common terms like that in math, what we can do is we can factor them out, right? We pull them out. So just for reference, in this example, I can factor out an x, right? And then what am I left over when I pull out an x? I'm left with y squared minus 1, right? If I do x divided by x, I'm left with 1. Right? So that's just kind of a hint. So up here, because both of these have a sign in them, right, we can factor out a sine. When I divide this by sine, I'm left with cosine squared. When I divide that by sine, I'm left with minus 1. So you may, something in your brain might be, oh, I recognize something there. It's okay if you don't. We haven't gotten comfortable enough with this yet. But this here, cosine squared minus 1, looks very similar to one of our Pythagorean identities. If I manipulate this, if I try to make it look like this, I can subtract 1 from both sides. And then I can subtract sine from both sides. Okay, here, right, this cosine squared minus 1, this Pythagorean theorem, this Pythagorean identity is telling me that I can replace cosine squared minus 1 with negative sine. I'm sorry, negative sine squared, right? That's part of our Pythagorean identity. So I factored out the sine, and then with the remaining expression, I made cosine squared minus 1 into negative sine squared. Now, because these two are both sines, I can multiply them together. And again, if I was treating them like variables, if I have x times x squared, right, when we multiply with exponents, we add the exponents together. So I would add my exponents. So the simplified version of sine cosine squared minus sine is negative sine to the third. Right? So they are equivalent expressions. Right? If I picked any angle and I plugged, 20 degrees into this one and I plugged 20 degrees into that one, they both get me the same value. Okay, any questions about that?
It's a little bit confusing, but I think I'll get the hang. Like you get the hang of it after some practice.
Yeah. So yeah, we're gonna spend some time on this because yeah, it takes a little time to get familiar with it. But like I said, if you kind of just think of them as their own separate variables, it boils it down a little bit. You get down to the base of it. But yeah, especially because the most you guys done before Precalculus is pretty much just SOHCAHTOA, which doesn't include this at all. So this is almost like a new language for you guys. So yeah, I'm expecting some difficulties in the beginning. And this part is just to kind of get you to feel the feel for moving on to the next part. All right. So when we simplify, let me add something. My hint, from dealing with this stuff for as long as I have, my hint for anything with dealing with trig is try to work with sine and cosine if you can. Those are our, they're kind of at the bottom of the pyramid of trigonometry. They're the base, they're the solid. You can't get any more simple than sine and cosine. So if you change everything to sine and cosine, then you can see the relationships and you can manipulate it a little easier than having to worry about, 1 plus cotangent squared equals cosecant squared, or 1 plus tangent squared equals secant squared, or some of the other rules that we'll learn later on. All right, so if you can get sine and cosines, they're a little easier to manipulate, and it might be, quicker to see the relationship between those. All right, let's take a look at okay, so like I was talking about before, like how these trig expressions act like variables, well, act like separate variables, right? So even though up here I have the same variable theta, sine behaves differently than cosine, okay? So they are kind of separate entities. So that allows us to do normal operations like we would see with normal variables. And one of those things is factoring. So if we have something where it's any trig function squared minus 1, whether or not it is involved with a Pythagorean identity, okay, we can always factor it, right? This is like saying x squared minus 1, right? This is a perfect square where we have one positive and one negative factor, right? X plus 1, x minus 1. So any trig function where it's, secant squared minus 1, I can break that up to secant plus 1 times secant minus 1. All right, straightforward like that. Now the difficulty is sometimes, let's see, do I have... So we do have a Pythagorean identity with secant, and that gives us something in terms of tangent, right? So I can manipulate secant. I could have moved this over here, right? And I can also say that this is equal to tangent squared, right? So that's where a lot of the difficulty comes in. If they just say straight up factor, right? You know, you can factor to this. But if we want to simplify it, they just tell you to simplify, then you can take it a few different ways. Now, what you're also going to do is you're going to look at the rest of the expression, right? So if the secant squared minus 1 was part of a bigger expression, then you would say, well, would it be beneficial for me to make it into a tangent? Do I see other tangents in there where they might eliminate each other? Or would it be beneficial to keep it in terms of secant and factor it like that? All right, so let's take, actually, let me see. I did have an example here. Oh, we only have 3 minutes. Crap. Okay, so let's pick this back up on, I don't want to get too crazy. Well, let's do one more. Let's do one more. All right, if we see something like this, where it kind of looks like a quadratic, okay, we can treat it like a quadratic, right? This would like be saying x squared plus 4x plus 4, right? So then you're looking for two terms that multiply to 4 and add to 4, right? So again, if you wanted to rewrite it, x squared plus x plus 4, 4x plus 4. So here we would just do a normal factorization as well. So I'd have tangent plus 2 times tangent plus 2, right? If I broke this up, it would be x plus 2 times x plus 2, which then I can rewrite as tangent plus 2 squared. All right, so this is, the very basic of it, and next week we'll take a look at the more complicated parts. I thought there's one more thing I wanted to say, but oh yes, I'm not targeting anybody right now. This is just from experiences in the past. Always make sure there's a variable or something after your trig function, right? If you write something like this without a theta or an x afterward, this makes no sense. Tangent by itself doesn't mean anything, all right? So, I know sometimes you might just forget the theta, especially if you're doing some division, like if you have sine over cosine, you might just write tangent and forget the theta, right? Just be careful. Your trig functions always have to have a variable after them. Okay, so that was just a side note that I just wanted to say. All right, guys. So we'll pick up with some more simplifications next week. Yeah, and have a good weekend, and I'll see you all on Monday.
Bye, you too.